We will begin the presentation on masked diffusion transformer with curriculum training. We became interested in rapidly growing LLMs like ChatGPT, which generate text autoregressively, token by token, limiting parallelism and causing potential error accumulation. To overcome these issues, we explored a diffusion-based language model inspired by denoising techniques in image and audio domains. This model uses two phases: masked reconstruction to learn sentence structure, and progressive denoising to gradually restore the original sentence. Unlike auto-regressive methods, this approach enables faster, more accurate generation. And this is the paper we referenced in our project. Let me briefly explain our pre-processing strategy for diffusion-based summarization. Since diffusion models learn to restore clean outputs from noisy inputs, our goal was to simulate that process during pre-processing. We do this by injecting different levels of noise into the summary, setting the original summary as the target and providing a mask ratio to indicate that noise level. Each data sample contains the article text, the masked summary, the target tokens only where masks occurred, and the mask ratio that guides the model's denoising. Now let's look at the two core components of our strategy. First, we apply random mask ratios from 0.2 to 0.8 to the summary. This helps the model learn to recover missing content under different noise levels, with mask ratio acting as a timestamp condition. Second, we use partial labeling. Only masked tokens are included in the loss, while the rest was ignored using -100. This focuses learning on the missing parts and makes supervision more efficient. Here's a quick example. With a mask ratio of 0.4, only the masked tokens like government and reduce are targets for reconstruction. Now let's move on to tokenization, a small detail but crucial for our setup. We chose the BERT word piece tokenizer because it fits our masking strategy well. It handles rare words using subword units and supports the mask token by default. More importantly, diffusion models rely on gradual restoration, so even masked subwords should remain learnable. Word piece gives us the consistency, allowing the model to reconstruct meaningful text step by step. We prepared two separate types of datasets, one for learning sentence structure and the other for article summarization. For sentence structure learning, we first decided to train the model on a simple dataset. For the simple dataset, we used tiny stories from Hugging Face, which contains simple storybook sentences. As for the complex dataset, we chose open web text, which includes news articles and other web texts, which was also used in training GPT-2. The dataset for sentence structure learning was organized as follows. It includes the following columns. Input ID is the tokenized sentence with masking applied. Attention mask is the column where, after truncating the mask length 128, paddings are marked with 0 and actual tokens are marked with 1. Labels contains the original target tokens that the model is supposed to predict. Mask rate indicates the applied masking ratio. And this is the masking function applied to the tiny stories dataset. For each masking ratio, the dataset size was about 8.5 gigabyte, and since we used 7 different masking ratios, we prepared about 59.5 gigabyte of data for sentence structure learning in total. Here's a quick overview of the masking function applied to the dataset for summarization. We start by tokenizing and truncating the summary. Now I'd like to dive to the pre-training process. First, let me explain our learning strategy. We adopted curriculum training approach. Unlike conventional masked language models, which use fixed masking probability, we start with a low mask probability and gradually increase it in stages. In each stage, we load a batch of input ID and corresponding labels. We identify masked tokens by checking where labels are not -100. These positions are tokens we have to predict. After feeding the inputs to the model, we compute the diffusion loss, perform backpropagation, and update the parameters. For each masking probability, we ran 2 epochs. We had 7 different mask probabilities, so we trained this dataset 14 times in total. Next, let's look at the model architecture. We begin with token embedding. The tokenized words from our dataset mapped into high-dimensional vectors inside the transformer, allowing the model to learn from them. In parallel, we use positional embedding, which is also mapped into vectors of the same dimension. Positional embedding tells each token's position because self-attention doesn't recognize the order alone. Rather than concatenating these two vectors, we add them to decrease the model size. By stacking this 6-layer transformer encoder layer, we created the full transformer encoder that handles both token content and positional information. Next, let's discuss how we calculated the loss. During training, our diffusion loss is computed on the masked tokens using cross-entropy. We sum the cross-entropy losses over all masked positions in the batch, then divide by the total number of masked tokens to get an average. If you look at the loss curves, you will notice that once the mask probability exceeds 50%, the loss starts to spike. That makes sense because with over half of the tokens masked, the model has fewer clues and more tokens to predict, which increases the error. Throughout training, the loss continued to decrease steadily, indicating that we didn't run into overfitting. Finally, let's see the response generation stage. We tried to follow as many ideas from the paper as possible. Pre-training was stochastically carving out blanks and filling them in. Response generation is more like the picture 3, where we sequentially fill in blanks until the passage is complete. To begin, we use a prompt once upon a time. This prompt is the prefix that goes into the model's input and then it generates what comes next. The model can't fill in the entire response perfectly in a single shot, so we used an iterative masking schedule. We started with a mask value of 1.0 and gradually decreased it down to 0.1 over 40 steps. For example, value 0.5, we randomly remask half of the tokens that have already been filled, then let the model predict those masked tokens again. Through this process of repeatedly masking and filling, the model adjusts its output bit by bit. That way, the final response emerges smoothly. And this is the result. Let me briefly introduce our second stage summary training process. Our initial model didn't generate summaries well, so we switched it to a pre-trained bird-to-bird model, which is compatible with our tokenizer. Although this model wasn't designed for diffusion and lacks a time variable, we tried to simulate a diffusion-like training method. The dataset was too large, so we downsized it for training, validation, and testing. We trained the model for 40 epochs, 300 steps per epoch with a batch size of 32. At first, masking ratios were selected randomly. Later, we applied curriculum learning, gradually increasing the mask ratio range over time. However, after epoch 33, validation loss began to increase, and final accuracy remained at about 16%. Raj scores were also low. When we tried to generate summaries, the outputs were mostly meaningless. The main issue was that bird-to-bird decoder is not autoregressive, which made it unsuitable for sentence generation. While switching models was an option, it required data reprocessing. Instead, we modified the training strategy using curriculum learning. Lastly, although we used Colab Pro, we ran out of compute resources and time, which limited further improvements. This is a demo video for our Phase 1 model. Thank you for listening.